Welcome to your AP Statistics lesson for chapter 28, chapter 18, sampling distribution models. Suppose we want to draw many samples and look at the distribution of sample proportions for these samples. The histogram we get, if we could see all the proportions from all possible samples from the same population, is called the sampling distribution of proportions. The histogram of the sample proportions would center around the true proportion P in the population. As far as the shape of the histogram goes, it would be unimodal and symmetric. In fact, it is just incredible that if the sample size is large enough, the normal model is just the right one for the histograms of sample proportions. All right, a sampling distribution model for how a sample proportion varies from sample to sample allows us to quantify that variation and the likelihood that we'd observe a sample proportion in any particular interval. To use a normal model, we need to specify two things: the mean and the standard deviation. So the mean of the sampling distribution model will be P, which is the proportion of the original distribution. And we will use the standard deviation of square root of P times Q over N. Remember, Q is 1 minus P. All right, so here we have a picture. We've got the mean of P in the middle, and then we go out 1 standard deviation from either side, 2 standard deviations from either side, 3 standard deviations on both sides of P. This should bring back memories of the empirical rule. And so we would expect 68% of the proportions to fall between 1 standard deviation below P and 1 standard deviation above P, and 95% to fall between 2 standard deviations below P and 2 standard deviations above P, and 99.7% within 3 standard deviations of the mean. So many polls will go ahead and give you their margin of error in terms of 95%. They'll go 2 standard deviation. They'll figure out what 2 standard deviations is, and they'll tell you that that's a margin of error. Okay. Polls will vary one from another. That's why you have to give a margin of error. And we call that sampling error. That doesn't mean you've done anything wrong. That's just acknowledging the fact that if we'd taken a different sample, we plausibly could have gotten a slightly different proportion. Another way of stating that, and probably a better way, is sampling variability. Again, the normal model just gets better and better as the sample size gets larger. Okay, so anytime we use a model, we have to make a couple of assumptions. And there are 2 we have to use here: the independence assumption and, like I just said, the sample size assumption. The independence assumption says that the sampled values must be independent of each other. That way, the likelihood of getting the results are not affected by the previous results attained. And the sample size assumption is that the sample size has to be large enough. Well, we can't check these explicitly, so we have to check corresponding conditions. Now, the independence assumption is checked by the first 2 conditions, and then making sure that the sample size is large enough is checked by the 3rd condition. Now, first thing we need to know is that the sample was formed from a random sample, preferably a simple random sample from the population. And that lets us believe that we've got a representative sample, or that we're much more likely to have a representative sample than a non-representative sample. We rarely sample with replacement. You rarely find that you count the same observation twice. So we just need to make sure that our probability of success isn't changing in any significant way, that we can use a model based on independence, even though there's a slight slight problem with the independence assumption because we are sampling without replacement, and that's by the 10% condition. It turns out we can act as though we are sampling with replacement as far as our model goes, as long as the sample size is no larger than 10% of the population. The change then in the individual likelihood of success is negligible. All right, success failure. In order for the sample size to be large enough, the expected number of successes and number of failures must be at least 10. And the way you check that is by doing your sample size times P, your probability of success, and your sample size times Q, Q being the probability of failure. So that'll give you the number of successes, the number of failures, and they need to be at least 10. So there is a range that works for us where the sample size is large enough, but not too large to where we can't act as though the sample proportions are independent from each other. Okay, so what does that mean for us? It means that a proportion is not just a computation from one set of data. It's also, we can think of it as a random variable quantity. And the random variable quantity follows the sampling distribution model for proportions. Even though we depend on sampling distribution models, we rarely get to see them. It's rare that somebody samples every possible sample of a certain size from a population. That would take a really long time in most cases. Usually we only think about them theoretically, or sometimes we have computers simulate them. They're important, however, because they act as a bridge from your real world data to the imaginary theoretical world of this statistical model, and that enables us to make an inference based on our data about the population. All right, so here we have our sampling distribution. Just one more time, just to reiterate, the mean value of all the sample proportions of all the p-hats is p, the population proportion. And the standard deviation of p-hat is given by the square root of p times q over n. All right, so now that's proportions. We're also going to look at means. Remember, proportions are for categorical variables. Now we're going to look at means. That's how we summarize quantitative variables. So, like any statistic computed from a random sample. So, proportions, standard deviations. Now that we're talking about quantitative data, still standard deviation, mean, median, all those things, first quartile, IQR, all those statistics computed from a random sample have a sampling distribution. Now, for now, we're just going to look at proportion versus mean. This time, let's look at a simulation just to kind of see how the shape of the sampling distribution is affected by the sample size. So let's start with a simulation of 10,000 tosses of a standard fair die, 6-sided die. And this time, we're going to have a sample size of 1. So just the outcome from one die being rolled. So the histogram looks like this. It's going to be basically a uniform histogram, uniform distribution. The value is going to be determined by what's on the left endpoint. So here's the number of 1s, here's the number of 2s, 3s, 4s, 5s, and 6s. All right, so what happens if we let n equal 2? We get a still symmetric, but no longer uniform. Okay, it's got a single peak right here in the middle. If we let n equal 3, it's going to be still symmetric, and it's going to get a little bit more bell-shaped. If n equals 5, it's starting to look more like a normal distribution. N equals 20, it looks like a normal distribution a lot. So that's the overall shape. Let's look at the spread. Okay, so the variability. So here in the first one, where n equals 1, it's spread evenly throughout. Even with n equals 2, the middle values are more likely. And in here, let's see, you can see that the variability is getting a little smaller more with the n equals 3. With n equals 5, the variability is much smaller. The extreme values are much less likely to happen. And then finally, with n equals 20, the variability has decreased tremendously, where the extreme values are extremely unlikely. You are very unlikely to get all sixes for 20 rolls, or for out of 20 dice. You're just rarely going to get all sixes. All right. As the sample size and number of dice gets larger, each sample average is more likely to be closer to the population mean. So we see the shape continuing to tighten around 3.5. And it probably does not shock you, like I said, as we were looking at them, that the sampling distribution of the sample mean becomes normal, or at least becomes more normal as n gets larger. In fact, the sampling distribution of any mean becomes more nearly normal, and it really should be more nearly normal. I should have a wiggle word right there, -1 for me, as the sample grows. All we need is for the observations to be independent and collected with randomization, and we don't even care about the shape of the population distribution. Remember, we have two distributions going on this time because the data themselves are numerical values. There is the distribution of the sample that generates the sample mean, and then there's the sampling distribution of the sample means. The fundamental theorem of statistics is called the central limit theorem. It has nothing to do with center values. It sounds like it would. It just means that it's fundamental. And the central limit theorem, which is used so frequently that we can use CLT to refer to it, states the mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. The larger the sample, the better the approximation will be. Now, like all good models and theorems, there are assumptions that need to be made. It's no surprise here that it's going to be an independent assumption and a sample size assumption. And again, we can't check those directly, so we go to our three favorite conditions. We check the randomization condition. The data must be sampled randomly. That allows for a couple of things. We know we have a representative sample, or that we're much more likely to have a representative sample, and that helps us act as though the values are independent. Typically, we don't use replacement, so the 10% condition keeps the sample size small enough that the likelihood of getting any particular value stays roughly the same. So when the sample is drawn without replacement, the sample size n should be no more than 10% of the population. But we don't want it to be too small. We need to make sure it's large enough. So the CLT doesn't tell us how large a sample we need. For now, you need to think about your sample size in the context of what you know about the population. When we look at means, we're doing inference for means again, we'll kind of nail down under different conditions how large the sample size needs to be. Okay. So the CLT says that the sampling distribution of any sample mean is approximately normal as long as the sample size is large enough. If the population mean of the individual observation is mu and the standard deviation is sigma, then the sampling distribution model of the sample means of size n is normal, or at least approximately normal, with a mean of mu and a standard deviation of sigma, the standard deviation of the original population over the square root of n. Okay, so what does this mean? All right, so you have a population, and you're going to take a random sample of a particular size. All right, let's say we're going to take this population, just keeps on going. We're going to do a sample size of 100. And we get a sample mean. Well, then we take another sample size of 100 and we get another sample mean, a sample size of 100 and we get another sample mean. Well, this original population has a population mean and a population standard deviation. The distribution of those sample means of the averages is going to have less variability than the distribution of the original population. And so the way we adjust for that is that you take the original population standard deviation and you divide by the square root of your sample size. So we would take the original population, since our sample size was 100, we divide by the square root of 100 or 10. Okay. Now the cool thing is the mean, the mu, the mean of the means, the x bars, is the mean. It's the same thing as the population mean. So the variability of this sampling distribution decreases as the sample size increases. In fact, it declines with the square root of the sample size n. So if you wanted to divide the standard deviation in half, you would need to use 4 times whatever sample size you've been using previously, because the square root of 4 is 2. Okay, so again, be careful. We have 2 distributions. Oh, there's Scout saying hello. We have 2 distributions to deal with. The first is the real world distribution of the sample, which we might display with a histogram. The second is the math world sampling distribution of the statistic, which we model with a normal model based on the central limit theorem. Don't confuse the two. So we could have a distribution, a nice little histogram, based on the 100 individuals that we choose from our population that gives us X bar. And then we will consider where X bar from that sample falls on all the possible values of X bar within this sampling distribution. Remember that the statistic itself is a random quantity. We can't know what it will be because it comes from a random sample. So we can't predict ahead of time. We can have a feeling for where it might lie, but we don't know for sure. Fortunately for the mean and proportion, the CLT tells us that we can model their sampling distribution directly with a normal model. There are 2 basic truths about sampling distributions. Sampling distributions arise because samples vary. You're going to get different results from different samples. Fortunately, they follow a pattern. And although we can always simulate a sampling distribution, the CLT saves us the trouble for means and proportions, because it tells us that as long as our sample size is large enough, the sampling distributions will follow an approximately normal distribution. Okay, so let's put these into practice. Let's look at problem 17 on page 434. I have it written out here. Best known for its testing program, ACT Incorporated also compiles data on a variety of issues in education. In 2004, the company reported that the national college freshman to sophomore retention rate held steady at 74% over the previous 4 years. Consider random samples of 400 freshmen who took the ACT. Use the 68, 95, 99.7 rule to describe the percentage of those students we expect to return to that school for their sophomore years. Do you think the appropriate conditions are met? All right, so here's what we're saying. We're checking to see if this model actually applies. Since it's talking about a retention rate, 74%, that's a proportion. P equals 0.74. So we are going to use the sampling distribution for sample proportions, which is going to be approximately normal and centered at P, and with a standard deviation of P times square root of P times Q over N. All right, so it's going to be centered at 0.740. Now we need to figure out the standard deviation. So square root of 0.74 times 0.26. Where did we get 0.26? 1 minus 0.74 over 400. And rounding to 3 decimal places, that gives us 0.022. So we're going to subtract 0.022 from 0.740. Then we're going to come back and add it to 0.740. And we're going to keep moving out in standard deviation units. And here we have our distribution. All right, so we expect 68% of all retention rates to be between 0.718 and 0.762, 95% to be between 0.696 and 0.784, and approximately 99.7% to be between 0.674 and 0.806. Let's see if the conditions are met. Let's check the randomization condition. Although not simple random samples, the problem does state that the samples are random samples of 400 college freshmen who took the ACT. It is plausible that the samples are representative of all college freshmen who took the ACT. 10% condition. It is reasonable that there are more than 10 times n, so 10 times 400, which is 4,000 college freshmen who took the ACT. Thus, the sample is no larger than 10% of the population. Success-failure condition. Since the number of successes n times p equals 400 times 0.74 equals 296, and the number of failures n times q, 400 times 0.26 equals 104, are both at least 10, the sample size is large enough for our methods. Now, you may be thinking, okay, Ms. Brown, why did you have to show the 10 times 400 and then the 400 times 0.74 and the 400 times 0.26? Well, I had to show it because I'm modeling for you how I want you to write it, how you need to write it for AP grading. The AP reader needs to know that you knew which values to take and put together to get the appropriate values, okay, to get the 4,000 college freshmen, to get the 296 successes, to get the 104 failures. They need to know that you took the correct values and worked with them. Based on the 74% national retention rate, does a college where 522 of 603 freshmen returned for the next year as a sophomore have a right to brag that it has an unusually high retention rate? Let's see how many standard deviations above or below the mean this observation is. That gives us a feeling for how likely or unlikely it is. All right, so here's our model again. It's at least approximately normal with a mean of 0.74. And now notice that we are using 603 as our denominator because now we're saying n is 603. It's no longer 400. So our standard deviation has changed to reflect that. And so our standard deviation is now 0.018. Our observation is reported to us as 522 of 603. So we need to divide to get the sample proportion. So 522 divided by 603 is 0.866. And now we can determine the number of standard deviations. So since our mean is 0.74 and our observation is 0.866, our z-score, the number of standard deviations our observation is from the mean, is equal to 7. So wow, any observation 7 standard deviations above the mean is unusual. In this case, in a good way. Okay, it's great to have 7 standard deviations more of your freshmen be able to come back for their sophomore year. So yes, the college has reason to brag. So how likely is such a rate? Well, good thing it's modeled by a normal distribution. We can actually figure that out. So normal CDF from 7 to infinity, just leaving it with the standard normal mean and standard deviation gives us 0. So not likely at all. This is exceptional. All right, so now we're going to assume that the duration of human pregnancies can be described by a normal model with a mean 266 days and standard deviation 16 days. So let's think about what our data would be here. It would be the length of pregnancy. So one lady may have 265 days, another lady may have 280 days with quantitative values. So it would make sense that we are talking about this sampling distribution of sample means when we're working with this. So, what percentage of pregnancies should last between 270 and 280 days? All right, well, let's figure that out. First, we need to find the z-score of our two endpoints. So the z-score associated with 270 days, when we subtract the mean and divide by our standard deviation, is 0.25. For 280 days, it's 0.875. So we just do normal CDF from 0.25 to 0.875, and we get 0.2105, so 21.05%. At least how many days should the longest 25% of all pregnancies last? So we want to do inverse normal of 1 minus 0.25 because it has to be the area to the left. So inverse normal of 0.75 and we get 0.67. We're going to plug that into our formula for the z-score to solve for the observation value. So 0.67 equals x minus 266 divided by 16. We do the algebra, multiply both sides by 16. We get 10.72 equals x minus 266. We add 266 to both sides and we get 276.72. And so 276.72 days or longer represent the longest 25% of all pregnancies. Suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. Let X bar represent the mean length of their pregnancies. According to the central limit theorem, what's the distribution of the mean X bar? Specify the model, mean, and standard deviation. It's going to be approximately normal with a mean, mu, and a standard deviation of the population standard deviation divided by the square root of the sample size. So 266 is the mean. Our standard deviation of our sampling distribution is 60 divided by the square root of 16. And so that should be 60 divided by 4. Oh, I had those backwards. This should be 16 divided by square root of 60. That's a typo. This should be 16 divided by square root of 60, and that's why that's 2.07. I have it correct right here, 16 divided by square root of 60. I'm sorry about that. So our probability that the sample mean is less than 260, we find our z-score. So our sample mean minus our population mean, 260 minus 266, divided by the sampling distribution standard deviation. So the original standard deviation 16 divided by square root of 60, and we get negative 6 over 2.07, which is negative 2.90. So saying we want the probability of X bar is less than 260, we have the probability that Z is less than negative 2.90, and we get 0.0019 or 0.19%. I don't know if you can hear her, but Scout is now that she's been let into the recording room, she is now asleep and snoring. All right, so 0.19%. All right. The duration of human pregnancies may not actually follow the normal model described in exercise 37. Explain why it may be somewhat skewed to the left. If the correct model is in fact skewed, does this change your answers to parts A, B, and C of exercise 37? Explain why or why not for each. Well, there are more premature births than there are extremely long pregnancies. Doctors typically do not let a woman go more than 2 weeks past her due date, and then they induce labor. So that would explain why they're somewhat skewed to the left. So, would our answers change? Well, yes, for parts A and B, as they rely on the normality of the distributions of individual pregnancies. And we're not taking sample means and looking at the sampling distribution there. We're looking at just distributions of individual pregnancies. So for part C, there's not going to be a change because the CLT, central limit theorem, guarantees a normal model for, or at least an approximately normal model for a sampling distribution with a sample size of 60, even if the distribution of the individuals is skewed. Okay, guys, sorry about that typo. Um, Go ahead and try your problems to try on your own, and we can go over this in class. And if you have any questions, remember, I'm never more than an email away. If you'd rather, you can just drop by my classroom and see if I can help you there. Thank you so much for watching the video. I hope you have a great day.